white slide. Oh, it says curtain and just great. Yeah. Anyway, it's just something to know about everything. And it gets backlit. Yeah, it's really dark back there. So sometimes it gets turned on. This will be backlit, so if it's a little dimmer. Plus, see black right there. That's actually part of the white. At first, I thought when he asked me to come in and made a streak on the screen, I was like, no, it's just $1,000 screen. And fortunately, it was just backlit. Okay, cool.
Sweet.
Oh, let us know if you need anything.
All right. Thank you so much.
Recording in progress.
All right, everybody. Sorry for the delay. Welcome back. Is my volume okay? Can you guys hear me? Fine in the back? Cool. All right. Sweet. So a few more weeks to the midterm here. Almost there. So goals for this week. Today we're going to continue sort of what we were doing last week in terms of kind of creating a model and comparing that to real world data. So we'll see some more examples of that today. On Friday, we basically did an example where there was two categories that we were comparing. I mean, really, when you have two categories, it's the same as having one category because, you know, the other one is just 100% minus whatever you have in the first category. So, you know, we did the example of the court case and then we did the genetics example. And basically, we're just trying to compare like some models assumptions about what percent should be in a category to what we actually observed. Today, we're going to do a very similar example, but instead of just two categories, there'll be like maybe 5 or 6 categories. And it's a similar type of thing where you're comparing like what's claimed to what actually happens. And this is basically going to bring us to this concept of hypothesis testing, which we've technically already done on Friday, but we'll just formalize the terminology around that. And then on Wednesday, we'll go into a little bit more details on hypothesis testing and what happens when things aren't that clear cut and like your data sort of matches the model, but like not really. So, what do we do in that gray area? We'll talk about that on Wednesday. And then on Friday, we'll go into our first set of hypothesis testing that involves numerical data. So thus far, we've been doing categorical data. On Friday, we'll do hypothesis testing with numerical data. Cool. Then a few announcements. So homework 6 due this Thursday, turn on Wednesday for a bonus point. And as I mentioned last week, please start this one early. So if you're someone who usually starts this a little bit later, try to get a head start on it. It is a little bit longer, so please get going on that. And then lab 6 is due Friday. So those are the main things there. Yeah, those are the main announcements. And then I guess one last thing I'll just mention is like, if you still haven't sorted out your midterm situation, like if there's a reason you can't attend the midterm for some sort of excuse absence, like please reach out to us ASAP so we can just get that all sorted out for you. Don't want to have to leave this to the last minute. Cool. All right. So just quick review on assessing models. This is basically where we left off on Friday. So we'll just kind of review sort of the general terminology here, the process, and then also just those 2 examples from Friday as well. So again, model is just a set of assumptions about data. And in data science, we call these chance models because they involve probabilities, they involve randomness. And the key question always is going to be, does the model fit the data? And that's going to be basically the key question throughout hypothesis testing as well. And so typically the way we will try to assess a model is we will first need to, first of all, you should define your model as something that's really explicit and you can simulate from. And because our step to assessment, the first step is to simulate data from that model. So, whatever assumptions someone is claiming, you need to be able to simulate from that. And then we want to simulate data from that and see what it predicts. And then what we're going to do is compare a bunch of simulations from the model to the actual data that we observed. So typically what's going to happen is like you have one sample of data that you observe. That's it. That's all you get. And maybe you'll generate some statistic from that one sample. And then you have your model, which you can just run all day and make like all kinds of simulations. So you'll have thousands and thousands of examples and thousands of statistics from every single sample that you simulate. And you're going to compare all those thousands to like just the one that you see. And then you basically want to see like, how crazy is this one that I saw? Is it look kind of like what I saw in the simulations, or does it look really different? And if it looks really different, then that means the set of assumptions that created those simulations probably isn't actually a valid reflection of reality. And that's basically hypothesis testing in a nutshell. Cool. So bringing that back to the 2 examples we did on Friday, typically what you're going to see with hypothesis testing is like there's some problem, some population we're trying to study, and there's going to be 2 viewpoints that we're assessing typically. And so just to kind of be really explicit about that for the examples from Friday. So in the jury selection example, basically the model, which is what was being claimed, was that the people on the jury panels were selected at random from the eligible population. So that was what was being claimed. This is very specific and very explicit because we knew what the eligible population was. It was 26% Black, I believe, at the time. And so that's specific enough to start simulating from. And so that was the model. And then we had the alternative viewpoint, which was no, it was biased against Black men. And so because the alternative viewpoint was that it was biased against Black men, what that means is we chose our statistic such that low values of what we observe would be in favor of the alternative. So in this particular case, our statistic was the proportion of people in a random sample that are actually Black. And so if we observe something that's low, that's evidence for the alternative that, it's biased against Black men. And so what we did was we chose that statistic, which is just percentage of the jury that's Black. We calculated that for a bunch of simulations. And then we also calculated that for our only example that we saw, which is the actual real sample. And then we saw that that was much lower than the values that were in our simulation. And so we concluded that basically the data that we observed is consistent with the alternative as opposed to the model. And then in our second example, which is the genetics case, the model, which was also pretty explicit, was saying that each plant has 75% chance of having purple flowers. All right, so that was what Mendel was claiming. And so we kind of used that to simulate a bunch of examples of plants and see what percent are purple in every single simulation. And then we compared that to our single sample that we had of actual observed plants. and saw that the value that we observed was pretty close to 75%. And so our alternative viewpoint in this case was that it's just not 75%. So it wasn't a particular direction. Notice the difference here, right? So the first example is a particular direction that we're talking about. In the genetics case, we weren't really saying the alternative is a particular direction. All we're saying is like, no, it's not 75%. So when you see something like that, where the alternative viewpoint is just like no, basically, then your statistic that you're going to choose to summarize your data isn't just going to be typically like a proportion. It's going to be like a distance of a proportion to that value. So in this case, what we did was we chose the percent that's purple and we subtracted 75% from it and then took the absolute value of that. So the reason we did that was because we wanted high, really, really high values and really, really low values are both evidence for the alternative in this case. All right. So when you see this in general, when you see the alternative like this, it means you want high values and low values. And so typically there's going to be some sort of absolute value involved. And so hopefully you're sort of seeing a little bit of a pattern there where basically this is going to be the general setup for hypothesis testing. There's going to be some model, some set of claims. There's going to be some alternative. And usually you should be able to interpret the alternative from the context of the question. And then you're going to choose a statistic to summarize your data such that extreme values of that statistic are evidence for the alternative. So that's the general process that we're doing here. And so sometimes the alternative will be something where it's like only low values matter or only high values matter, or there's going to be situations where both high and low values matter. If that happens, you can sort of combine them together by just doing absolute value. All right, that's the main kind of setup. Cool. Any questions about that? All right. Cool. And then this slide is just basically summarizing what I just said, but basically we want to choose a statistic to measure the discrepancy between the model and the data. So sometimes that could be as simple as just proportion that are in a category. Sometimes it's proportion minus some value, absolute value of that. And then once you've chosen your statistic, make sure you go and simulate that statistic from your model. And then you basically evaluate that actual statistic on the sample data that you've observed. And then oftentimes we'll just draw a histogram of the simulated values, which is what we've been doing so far. So basically simulate this statistic many, many times, which basically gives you a sense of like, how does this statistic vary under the model's assumptions? Because remember, we talked about how a statistic itself is a random quantity. So it kind of moves around. So like, we have this one sample, but maybe we just got unlucky. Like maybe the statistic we calculated was just really low by chance. And so to evaluate whether that's just lucky, what you do is you simulate many, many times from the model's assumptions to get a sense of how variable it is. And then that'll give you a sense of like, is this really lucky or is something else going on? And then oftentimes just comparing your observed value to the histogram is enough. Like if your observed value is really, really far outside the histogram of your simulated values, you can be pretty confident that your data is consistent with the alternative. There will be situations where sometimes your observed value kind of overlaps a little bit on the edge of the histogram, things like that. We'll talk more about that on Wednesday. But in general, a histogram should suffice. Cool. So with that, let's try to do a couple of discussion questions here. And so again, we'll just like last time, talk to the person next to you. And we're just going over two situations here. So in both of these, we want to choose a statistic that's going to help us decide between these two viewpoints of the world. And the data we're going to have is results of 400 tosses of a coin. And so in the first example, we're going to have basically two viewpoints. One is that the coin is fair. And then the alternative viewpoint is no, it's not. And then the second, which is like a completely different test, is the coin is fair or no, it's biased towards heads. So with these in mind, choose a statistic that will help you decide between the two viewpoints in each of these problems. So basically you should be coming up with one statistic for problem A and then a completely different statistic for problem B. All right, so let's take a couple of minutes, talk to the person next to you, and then we can try to go over the answers together. Okay. That was interesting. It was like all of a sudden everybody got really quiet. So I feel like you guys got it. All right. So any guesses, any thoughts for part A? What'd you guys come up with? Anybody want to share? As your test statistic? Come on, I can wait here all day. Any suggestion, any guess? It's fine. Don't be afraid. Yeah. What's that? Oh no, sorry. So the question is to choose a statistic for each one, like come up with a statistic for each one. So similar to like what we did so far, right? Like so in the first example, we did like our statistic was a proportion that's black, and the second one is proportion that's purple minus 75 absolute value. So this should be some sort of like mathematical expression, basically. So for part A, I guess, what mathematical expression did you come up with, or like how did you choose to summarize your data? Yeah. Roughly 50% would be heads, 50% would be tails. Yeah, so that's, I mean, you're kind of alluding to a statistic in that case. So that's pretty close. I think what you're kind of basically saying is like, what's the percent that should be heads? So, you should be expecting 50%. So what you're saying is basically like what the statistic should probably look like under the null hypothesis. And the statistic itself is actually just a proportion of heads. So that's really kind of what you should be saying for the for part A. And then it's actually just proportion of head. In this case, because the alternative is like, no, it's not. What you want to do is take that proportion of heads and subtract 50. So that's where the 50 comes from, and then take an absolute value of that. And the reason for that is because if this is a fair coin, you're going to see, like she said, it's going to be mostly 50% heads, 50% tails. If it's an unbiased coin, let's say it's biased towards heads, you're going to get a lot more heads. If it's biased towards tails, you're going to get a lot more tails. So like a really low percentage of heads. So basically, like if you observe anything that's far from 50%, that's evidence for the alternative. If you observe stuff that's close to 50%, that's evidence for kind of the model. And so because of that, you want to choose your statistics so that extreme values are for the alternative. And so in this case, what we'd actually try to do is calculate the proportion that's heads, subtract 50% from that, and then take the absolute value. So for example, let's say we observe like 90% heads in our actual data set, then the value of the statistic would be 90 minus 50, and then absolute value of that, which is 40. And then similarly, if I observe like something super low, like 10%, I would also get a value of 40. So, both really, really high values and really, really low values are going to both convert into a number that's just really far from zero effectively. And then for B, you have the situation where your coin is fair, but then the alternative is no, it's biased towards heads. And then you want your statistic to be such that, extreme values of it are evidence for the alternative. And so the alternative, it's biased towards heads. That means basically just like higher values of a proportion of heads is going to result in evidence for the alternative. And so that would be for part B, which you could just use the proportion of heads on its own, and you wouldn't have to do anything else actually. And so just to show these to you guys here, basically for both A and B, the percent of heads is a good starting point, but it might need adjustment, especially for part A, because if you just had like low percentage of heads, that's not really going to work that well for part A. So you want to convert that into a large number. And so we can do that using absolute value. And so for part A, it's basically the distance from 50%. That's what's important for part A, because that ensures that both really low values and really high values are evidence for the alternative. And then for part B, you can just use the percentage of heads alone, and that's fine. So does that make sense? The difference in like why we use one versus the other in those situations? Any questions about that? I'm happy to clarify. Yeah. What's that? Yeah, extreme values is just like things that feel like kind of crazy. Like if your coin is fair, right, and like you tossed it 400 times, and you got like 90% of them are heads, like that seems a little bit weird. It's kind of fishy, right? So that's what I mean by extreme. So like 90% would be really weird in that situation, and 10% would also be really weird. And both of those would be evidence for the alternative that it's not fair. If you look at the second problem, right, let's look at those same hypothetical scenarios, but in the second problem. So in the second problem, the alternative is that it's biased towards heads. So if you see 90% heads, that seems like maybe it's biased towards heads. If you see 10% heads, then that's not really evidence for alternative. In fact, that's actually more evidence for the model, because the alternative in that case is just it's biased towards heads. So there's a slight difference there. So like getting 10% versus getting 90%, those actually mean different things in both of these problems because of what the alternative is stating. So you need to basically choose your statistic. You need to summarize your data based on what the alternative is saying. Cool. Any other questions about that? All right. So yeah, don't worry if you didn't get that right away. We're gonna do this again and again this week, and there'll be lots more examples of this and other questions. I mean, we'll definitely talk about this more like in lab as well. All right, so for today's example, what we're going to be doing is, again, it's a categorical data set, but in this case, we're going to have more than 2 categories. And so it gets a little bit more interesting, a little bit different, the way that we actually calculate our statistic. And so this is another jury selection example. It's actually here in Alameda County. And so this is from, looks like 2010, so not too long ago. But it's kind of a similar sort of case where we're looking at kind of racial ethnic disparities in what was actually selected versus what's actually eligible in the population. And in this case, we're going to be looking at more than just 2 categories. And so I won't walk through this because you guys should be familiar with this based on kind of what we talked about in the last week's case. But you know, you have your list of eligible residents, and then from that, a jury panel should be selected, which is kind of should be representative of your eligible residents. And we talked about how representative basically means like should be like a random sample. And then there's usually some additional deliberation, interview questions, things like that, that bring the jury panel down to just the jury. And I won't go too much into all this either, but it's very similar to what we talked about last time. And you know, the idea is, at least at this step from the list of eligible residents, the jury panel, that should really look like a representative sample from your population. So that's really the key here. And so in this case, we're looking now at, you know, multiple categories. So we have like maybe 5 like ethnicities, let's say, that we're talking about here, rather than just 2. And so, you know, the question is actually basically the same. It's like, is our jury panel representative of the population or is it not? Those are basically the 2 viewpoints here. And so again, this is a situation where our alternative viewpoint is just like, no, it's not. And so because of that, you know, you want your statistic to be basically such that positive values of it are evidence for the alternative, and like values close to 0 are evidence for the model. And this is very unique because the alternative is just like, no, it's not. So it's just like not true. And so in the case of like the jury panel last week, we just had 2 categories. And so all we really had to do is just look at that one category and like see what was the proportion of the jury panel in that one category in our data, and then compare that in our simulation. And that was like basically it. We had to just pay attention to one category. But in this case, we're going to have like 5 categories. And so, you know, how do we assess whether the proportion in those 5 categories is the same as our, you know, simulation or not? It's a little bit trickier because like you could have one category that's like a little bit higher than what we expected, and then another category that's like a little bit lower. There's like 5 different things basically going on. So it's like a little bit more complicated, but we still need to take account all those 5 differences and summarize it into one number ultimately. That's the way this hypothesis test always has to work. We have to summarize our data, no matter how complex it is, into a single number. And so it's a little bit tricky with like 5 categories, right? And so what we're going to do is basically come up with a metric to do that, which is going to calculate the distance between distributions. But before I get into that, I guess, let's actually just look at the data because that's helpful to just take a look at first. So I'm just going to zoom in here a little bit. So these are going to be our categories for this problem. And so we have the 5 categories right here. And then in this second row here, we have, or second line, I should say, we have the eligible proportions. So these are the proportions in each of the categories within the actual county at that time of eligible jurors. And so this should sum up to 1. This all 5 of these numbers should sum up to 1. And then the actual panels that we're kind of randomly sampled from this eligible population look like this. Right, and so for example, we have like 26% Asian in the panel, whereas in the actual eligible population, it was 15%. So you can see a little bit of a difference there. And again, the question is, that difference seems pretty high, 15 to 26, but like maybe that's possible. Like it could happen by chance, just happen to get a lot of Asian people in the particular sample, right? So it's totally possible. But we have to understand like how possible is it probabilistically? Is this really crazy, or is this kind of within the realms of kind of reality and what we would expect? So we're basically putting all these numbers together into this table, so we can just see them all side by side. So again, here we can just see all the different categories, the eligible proportions, and then the panel proportions, which is like what was actually observed. And so we have enough information now to basically like create a model and simulate from it. And this might be a little bit more helpful to look at if we make an actual histogram, or sorry, bar chart, not histogram. These are categories. So we're going to do jury.bar H, ethnicity. And so we see here the different ethnicities. So it's a little bit easier to see it this way. And so we have each of the categories going down on the vertical axis, and then we can see the bars for each category, both in the eligible population and in the actual panels. And so visually, it's a little bit easier to see here. And then what we're going to do is we're going to just take the values from the model, which is basically the eligible population. I'm just going to put that into its own name called model. And this is what we're going to use to simulate data. So I'm just putting these same values again into this other name model. And then what we're going to do is use this to simulate some data. And so how are we going to simulate data? We're just going to use sample proportions again. So sample proportions, it's the same thing that we used last time on Friday. In this case, we have 5 categories instead of 2, but it works exactly the same way. So I'm going to call this simulated to do an example of this, and we're going to call sample proportions. And we're going to pass in the sample size. So in this case, the sample size was actually 1,423. So I forgot to mention that, but that's pretty important. So fairly large sample size. And then we just pass in the model, which is the proportions I just defined above. And so if I run this, we can simulate some data. And so again, how does simple proportions work? It does several steps under the hood. So it does a sample of 1,423 people from a population, assuming that these are proportions in the population, and then it returns the proportion in our sample that are in each of the categories. So in this particular run that I just did, we happened to get 14% of the sample was Asian, just as an example there. And so I could run this again, and you can see how these numbers jump around. So every time I run this, all the numbers move a little bit, which is to be expected. And so really the question is, we're doing some simulations here, and the question is like, our eligible population versus our panel that we actually observed, how different is the panel we observed from these simulated values? That's really the question we're trying to answer. And so let's actually just put all this together so we can see just an example of like a single run of the simulation. And we're going to do this like 10,000 times, but let's just start with one. So we're going to call this jury with simulated, and we're just going to do jury with column, and I'm just going to add a new column with a single simulation, just so we can see it visually. And then I'll just show this again here below. And so this way you can just see them all kind of together side by side. So here we have kind of the model, which is the eligible population. We have our observed data, which is our single observed data. And then we have a run from the simulation, so a single simulation. And basically we're going to want to do this simulation many, many times. And the point is to compare the panels to the simulated. We don't really need to compare the panels to the eligible, because the eligible is this like theoretical thing. And we don't expect the panels to be the same as the eligible. That's fine. It's a random sample. It's not going to be exactly the same. But the point is, how different is our observed data from the simulated? That's really what's going to come down to, right? Cool. So in terms of finding a difference between them, that's where it gets a little bit tricky, right? So if I wanted to summarize all these panels as like one number, or summarize all these simulated values as one number, or even just summarize like the difference between these two as one number, it gets a little bit tricky. Like I need to basically summarize the difference between these two columns as a single number. Any guesses, like any thoughts on how we could try to do that? Like, is there some sort of mathematical expression, some sort of math I could do to basically like, that would quantify like how different these two columns are? Any thoughts? Yeah. Yes, well, yes, you could use a total variation distance, which is what we are going to end up using. It's basically a concept of distance. That's really what it comes down to. So it's like, how far apart are these columns? Like, are each individual value like really, really far apart, or are they really, really close? So like one thing you could do maybe as a first guess would be like, let's just take one column and like subtract the other column. And then just like sum that up or something. Like that could be one simple way to do it, right? Any guesses as to like why that wouldn't work? Taking the sum of one of these columns and subtracting the sum of another column. It seems good in like just theory, but any guesses? It's pretty subtle. Yeah. You might be adding positive, negative values. That's true. In this particular case, what's nice is because this is a categorical distribution, we do know that each column is going to be all like at least 0 because each value in the column is like a proportion. So we know it's going to be between 0 and 1, every single value. But yeah, that's a good point in general. If you were taking like the difference of two columns, that would be a concern. Thankfully, we don't have to worry about that here because we do know that these are categorical data in each column. So we're good there. So for this particular case, that's actually okay. So we know they're going to be greater than 0. Any other guesses? Like what's an issue? Yeah, the sum of all the columns is going to be 1. That's actually the biggest issue in this particular case. So this is actually, that's an issue that's particular to our example, but not usually an issue. But the way this is defined is that we need all the categories to sum to 1. So this entire panels column is going to sum to 1, and this entire simulated column is going to sum to 1 every single time. Like every single time you run this simulation, that entire column needs to sum to 1. That's just like definition of categorical distribution. And so if I was to simply just like subtract this column from this one and add it up, I'm just going to get 0 every time. So that's not that useful. So it sounds like it would work, but unfortunately doesn't in this case. And so we have to do something a little bit different, which is specifically for this situation of like distributions. And so basically the idea what we're trying to do here is, we're trying to measure the distance between these two distributions. We can't simply just like subtract because that's going to give us like values of 0. And so what we're going to do is the total variation distance. This is like a specific terminology in statistics. And so basically the way it works is it's multiple steps. So the first step is for each category that you have, compute the difference in proportions between the two distributions. So it's basically take the first column and subtract the second column. So that's the first step. But before you add everything together, there's a few additional steps. So firstly, you take the absolute value of the difference. So first column minus second column, then take the absolute value, then take the sum and then divide by 2. The divide by 2 isn't that important here. The main thing that we did differently really is just the second step, where we took the absolute value. So when you take that absolute value, that ensures that this isn't going to add up to 0. And the reason for that, if you think about it, is like these distributions, the way they work is like, one of the categories might be a little bit higher, but another category might be a little bit lower. We know that both of the columns are going to sum up to 1, but we know for sure that like some rows are going to be larger than another, some rows are going to be smaller. So some of these differences will be positive, some will be negative, pretty much every single time. And if we take absolute value, that just ensures they're all positive. And then we can sum them up safely without things adding up to 0. And this is actually an interesting statistic now. And so we can actually do this in Python. So I'll break it down in steps 2 here as well. We're just going to make a function for this. So we're going to call this TVD, total variation distance. And then basically as inputs to this function, it's going to expect 2 things. So one is our first distribution. Again, distribution is really just in this case, just like an array of proportions. And then another array of proportions for another distribution. And then what is it going to return? So we're going to do the exact math I just mentioned. So first step is take your first distribution, subtract the second one. Then what we're going to do is take the absolute value of that, because we know that we can't simply subtract them because it's going to sum up to 0. So let's take the absolute value of the difference. Once we've taken the absolute value of the difference, now we can sum up everything. So we sum up the entire kind of new column that's created. And then in the end, we divide by 2. And so this is going to basically be how our function works. And so if we wanted to actually calculate this for our single observed value, we could do this actually. So what we could do is, I'm going to call this observed TVD. And so I'm actually going to run this function on jury.column panels, which is what we observed, and then jury.column eligible, which is kind of our eligible population. And so we expect there to be some difference here because again, the panel, even if the model is true, the panel is supposed to be a random sample from the eligible population. It's not going to be exactly the same. It might be a little bit different. So we should expect some difference here. And we can take a look at what the actual value is. So we run this, we get a value of 0.14. So what does this mean? Like, is that large? I don't know. It could be, but we don't really know yet. And what we need to do is we need to replace this, what we observed, with a simulated panel. That's what we need to do. We need to do the same process, but with a simulated panel, compute its total elevation distance from the model, and then do that many, many times, and then see how big is 0.14. Maybe 0.14 is like totally reasonable, and like that would definitely happen just by chance. And this we'll go through the process of actually evaluating that. But now we actually at least have a way to sort of quantify like how crazy each simulation is, or how crazy our data is. That's really what we need to do. That's what our statistic lets us do. So any questions about that? Cool. And so we can actually just do this with the example that we already had. So we already saved this in the table, simulated. So I can actually just run this with the simulated column just to give you a sense of like what it looks like. Oh no. Simulated is not in the table. Okay, I probably used the wrong table name. Yeah, okay, very good, simulated. Let's try this again. There we go. So for this particular simulation, the distance, total elevation distance from the kind of model, the sort of theoretical thing that should be happening was 0.011. And so this is just one simulation. Again, this value is a lot lower than what we observed, but we still don't really know if this is super big. It could have just been a chance that our simulation happened to be very close to the eligible population. So, you know, to really do this robustly, we need to do this many, many times using a for loop. And so that's what we'll do next. So firstly, we're going to create a function to help us with this, which is going to create a simulated total variation distance. And the way it's going to work is it's going to call the TVD function on a new simulation. And we can create a new simulation just using sample proportions with our sample size and our model, which is an array. So just look at model again, just to show you guys. So that's the array of the kind of true proportions in the eligible population. So what we're going to do is create a simulation from that model, and then take the total variation distance between the simulation and the model. And this will give us a distance of like the simulation from the model. And again, this is useful to do because our simulation is a random sample. It's not supposed to be exactly the same as the model. There is some variability there. And so we just want to quantify that. So now we have a function to help us do that. And this basically like simulates a jury panel, computes the distance from the eligible population. And then now we're just going to do this many, many times. So I'm going to make an array called TVDs, which is just going to store all of our TVDs from our simulation. Let's do 10,000 simulations. And then we'll do a for loop to basically do the simulation again and again. So np.arange num simulations. And then in each for loop, what we're going to do, so we're going to generate a new TVD, which is just going to be determined by simulated TVD, assign that to new TVD, and then just append this to the array. So this should look somewhat redundant at this point. We've done this so many times now, but this is basically always kind of the name of the game when we're doing hypothesis testing. So it's like figure out a way to come up with a simulation of your test statistic. Once you've done that, write a for loop, just do it a bunch of times and add it to an array. All right, so this is the same thing we've done kind of before. And so now we've run this. And then finally, once we run this, we can now create a plot. So let's make a chart here. I'm going to call the title simulated TVDs if the model is true. So that's the key thing here, right? And then I'm just going to put some bins here so we can visualize this. So we'll do 0.05 to 0.005. Or sorry, 0 to 0.005 in increments of 0.0005, because these are pretty small. These values, TVDs typically aren't going to be that large. So we don't need like super big range here. And then we'll do table with column. We're just going to create a new table with all the simulated values. I'm just going to pass in the name of the column as the title of our plot. Doesn't matter too much. And then we're going to do a histogram of that using our bins that we just defined. And so we can take a look at this. So this is our final histogram of all of our simulated values. So again, just to recap the process, what did we just do? We simulated jury panel from our eligible population. We computed the total variation distance of each simulation to the eligible population. So like simulation, compute TVD, simulation, compute its own TVD, simulation, compute its own TVD. We did this 10,000 times. Now we have a histogram of all 10,000 TVDs. And so now we have a sense of like how your jury panel should vary as you sample from it randomly again and again. Sometimes the distribution looks really, really different all the way over here. This is a value that would be very, very different. Sometimes it looks really, really close to the eligible population. Most of the time, it's a little bit different. It should be a little bit different. It's a random sample. It's not going to be exactly the same. But the point is we have a sense of variability now. And then if we go back to our original value, what we actually observed, the observed value, let's actually take a look at that. So what was our observed value in our actual data set? Just observed TVD. Oh wait, that's not the observed value. Sorry, I must have reassigned it. Yeah, this should have been simulated. Okay, this is the observed value. Run this again. There we go. So our observed value is 0.14. And as we can see on this histogram, 0.14 is like way, way, way out to the right here. And so this is another case where basically what we observed is really, really far from the model. And it's so far that like, even if we simulated from the model 10,000 times, we never see anything as extreme as that. And so this is just another way of doing a hypothesis test, basically. So in this case, we see that what we observed is very far from kind of reality. And so those assumptions probably aren't true. And so that's kind of the conclusion of our test in this case. So any questions about that? Yeah. Yeah, I mean, that's a good question. So when things are that far apart, does that mean like something was wrong with the model itself, or was something wrong with like the process of the jury selection? So in this case, like our model basically is saying that the process of the jury selection was a random selection. That all of those assumptions are part of the model actually. And so something in those set of assumptions is wrong. Either the random selection wasn't actually random, or maybe our data about the eligible population is wrong. There could be a lot of things wrong. We're not really saying like what's wrong in the entire process, but like something's definitely wrong. That's what we're saying. Yeah, good question. Any other questions? Cool. All right. So that's our kind of third hypothesis test, I guess I should say by now. Sweet. So just a summary of the method again. Basically what we were trying to do was assess whether a sample was randomly drawn from some known categorical distribution. That's the eligible population. How do we do this? Well, we use the TVD as our test statistic because it measures the distance between categorical distributions. So basically it allowed us to measure like categorical distribution of a sample from categorical distribution of a population. Sampled at random from the population many, many times, basically simulated, computed the TVD of every single simulation, and then compared the empirical distribution of the simulated TVDs to the actual TVD in the sample. All right, and this gives us a sense of like how crazy that sample really was. And so this whole process that we've been doing today and Friday is just called hypothesis testing. And so just to kind of go over some just general terminology and procedure here, basically this test chooses between two views of how the data is generated. Both of these views are called hypotheses. And so the test basically picks the hypothesis that's better supported by the observed data. So that's basically what we've been doing so far, just adding some terminology here. And so typically in the context of hypothesis testing, we're going to call those two viewpoints of the world, the null and the alternative. And so this method only works if we can simulate data under one of those hypotheses. And usually it's the null. Usually the null is the one that's like super, super specific that we can simulate from. And oftentimes the alternative is like a little bit more generic and not quite specific enough to simulate from. And that's totally fine. But it's just important to be able to simulate from one of them. Typically the one we can simulate from is the null. And so, under that assumption, basically the null hypothesis is kind of this really well-defined chance model about how the data was generated. And we simulate data under those assumptions, and that's called like simulating under the null hypothesis. So a lot of times you'll hear us say that, simulate under the null. That's basically what that means. So for example, in like today's example, what we did was we had those eligible population categories. And so our null hypothesis was that this is a random sample from that eligible population, and that eligible population is a categorical distribution, and we can use sample proportions to sample from it, to simulate from it. So that's all like super well defined. It's a very, very explicit chance model that we're basically created there. And then the alternative hypothesis was that no, it's not. And so that's very generic. Like if you say no, it's not, like it could be literally any other distribution, right? So that's not specific enough. We can't simulate from this alternative. It's just way too broad. That's okay, but just important to keep that in mind. Only one of these is really like super explicit. The other one is very, very generic. And then the key is, once you have your null defined, once you have your alternative defined, you need to come up with a test statistic, or a statistic which like summarizes your data. And that statistic needs to be chosen such that extreme values, really weird kind of values, are evidence for the alternative. That's kind of the general process we're going to follow. And so your statistic that you choose is all like kind of fully dependent on what the alternative was. And if you're not totally clear on that, just take a look at the discussion question again, because the discussion question had the exact same null hypothesis in both examples. The only thing that was different was the alternative. So the alternative completely defines the statistic. And so in this context of hypothesis testing, we typically call this statistic the test statistic. And it's really just in the context of hypothesis testing, but it's basically the one that we choose to simulate. It's the one that we're going to also calculate from our random sample. And it's the one that helps us to decide between the two hypotheses. And so the main questions to think about when you're trying to choose a statistic is like, what values are going to make us lean towards the null? What values are going to make us lean towards the alternative? And so ideally, you want to answer the second question and really think about like, I preferably want the answer to just be high. Like ideally, I just want high values of the statistic to be evidence for the alternative. If you have a situation where it's like both high and low values are evidence for the alternative, that's a little bit problematic. And that's a situation where you should try to probably like sneak in an absolute value or something to try to make it all just positive. And that's what we ended up doing for the genetics example, because the genetics example again was like 75% with purple, alternative is no, it's not. So therefore, if it's not purple, if it's not 75%, like really, really high values, like 100 should be evidence for the alternative, but also really low values, like 50 should be evidence for the alternative as well. And so the only way to combine that into one is to just take either of those values, subtract 50, and then take the absolute value. So that just gives you like a distance to 50 effectively. And so always try to make it so it's just like one side, like either really, really high values or really, really low values or evidence for the alternative. That's just really, really important when you're choosing your statistic. Cool. And then so once you've chosen your statistic, then what you need to do is just go through the simulation process. That's kind of the last step. And that's what we've done many, many times now. So basically simulate that statistic that you've chosen under the null hypothesis. So basically like under the assumptions of the null model, assuming that it's basically true, simulate many, many values, draw the histogram of those simulated values. And that histogram that you're observing is basically the empirical distribution of the statistic, assuming the null is true. So that's kind of like what should happen if the null is true. And then what we can do is basically compare that to what the actual value that we observed is. And then one kind of really minor detail to mention here is that that empirical distribution you're seeing, it's an approximation. It's not the actual like probability of seeing like a particular value. So actually, if I go back to that histogram, it's just worth mentioning this. So the height of this bar that's here, this isn't really like the true probability of seeing a TVD that's at this level. I don't know what value this is, like let's say between 0.015 and 0.02. It's the observed value. We did a simulation. This is an actual observation. If someone went out and did another simulation of 10,000 values, their histogram is going to look slightly different. But as we know from the law of large numbers, it should look pretty similar. So as long as we do a large enough sample size, this distribution should look basically the same no matter who repeats our study. And that's the key point. We don't really have a way to find like the theoretical distribution And the best we can do is an empirical. So that's just a small note worth mentioning there. But that's still okay because it's a large sample size. And we can be pretty confident it's like basically the same. Cool. So yeah, I think that's basically for null hypothesis and alternative, how to assess it. And we'll be using this terminology more and more throughout the rest of the semester. Thanks.